As I said before, binary search trees are a great structure in terms of allowing us to, for example, print all the elements in sorted order, in terms of allowing us to find an element in the list and so on. However, as the structure of that tree becomes more like a chain, all the elements are basically on one long path from the root to a leaf. The operations like searching in the tree and adding, inserting to it, or deleting from it could become problematic there. And it's very important that now we try to expand or add more constraints on binary search trees to allow us to maintain a property, as I said before, that the height of the tree is on the order of the log of the number of nodes in the tree. Because once we have this, then operations like search or insert or delete, they will take on the order of log n, and things are great. Again, as I said before, we cannot continue to decrease h below log n. Okay, so we would like to get to a tree structure. It's binary search tree, but with additional properties that will guarantee that the height of the tree is on the order of log n. And one of the most famous structures for this is known as red-black trees. Red-black trees. Okay, I will use the acronym RBT. Okay, so what is a red-black tree? It is a binary search tree with additional properties. Okay, so let me actually draw a red-black tree here. So let's consider this node here has the... First, I need again to maintain it is a binary search tree. So imagine that this is 20, this is 10 here, this is 15, and this is, let's say, 1 and 5. And here, let's say we have 30, and we have 25, we have 40, 35, and 70. And then for every node on the leaves, we also make sure that when we don't have any children, we explicitly put nil here, and it will be clear very soon why. I will put nil here, the same thing, nil, the same thing here. So these are all nil. Okay, so red-black tree has to satisfy the multiple properties. The first one is, as the name indicates, every node is either red or black. Okay, so nodes will have colors. Okay, so you can imagine that a node has a flag with it, or a variable C for color. And as before we had x.key, x.left, x.right, imagine now that it has x.color as well. So x.color is the color of that node. And every node is going to be black or red. So let me actually color a few of them red. So let's think about this being red and this being red. Let me take this to be red here, and let me take these two to be red. Okay, so now if you think about these, the nodes in this tree, each of them is either black or red, and we have additional properties. The second one is the root has to be black. Okay, the root is black. The third one, these are all the trivial ones so far. The third one is that every leaf is black. Okay, so notice here that all the leaves in this tree are the nil. Okay, so they are all black. Okay, there are no leaves that have actual key in them. Now we come to the two most important properties. The fourth property is if a node is red, then both children are black. Then both its children are black. Okay, so if you look at the tree I drew here, the node with the key 10, it's red, the children are black. If you look at 5, it's red, the children are black. If you look at 30, it is red, the children are black. If you look at 35, both children are black. If you look at 70, both children are black. Okay, so we want to maintain this one. The fifth property is that for every node, for each node, all simple paths from the node to descendant leaves must have the same number of black nodes. Must have the same number of black nodes. Okay, so if you look at any node in this tree that I drew, look at all the paths that go from that node to any leaf under it. All these paths must have the same number of black nodes. So let's actually take as just one example here. Let's take the node 10, for example. Look at all paths that go from 10 to a leaf. So this is one path. It has 2 black nodes on it, 1 and nil. Look at this path. It has 2 black nodes, 1 and nil. Look at this path. It has 2 black nodes, 1 and nil. Look at this path. It has 2 black nodes, 15 and nil. Look at this path. It has 2 black nodes, 15 and nil. If I did my things right here, I believe you can actually verify it for all nodes in this tree, and you will see that it satisfies these five properties. Okay, so a red-black tree must satisfy 5 properties, the first 3 of which are basically trivial, that every node is either red or black. We want the root to be black, and every leaf is black. Okay, we could have reversed actually the colors here. We could have said the root is red, every leaf is red, and then we have to be careful about conditions 4 and 5. Okay, but 4 and 5 are the more important ones that actually are going to play a big role in guaranteeing certain properties of this tree, and both of these properties will actually cause us a slight headache when we are trying to insert or remove elements to this kind of tree. The fourth one is that if a node is red, both children have to be black. So we cannot have 2 red nodes in a row. So we cannot have a node being red and one of its children is red. So if the node is red, that both children have to be black. Second thing is that if you look at a node, any node in the tree, look at all the paths emanating from that node towards the leaves. All these paths must have the same number of black nodes with respect to that node. Okay, because once you look at a different node, the number of black nodes on a path from that node to leaf is going to be a different thing, but it must be the same number for all paths from that node. Okay, so this is what a red-black tree is. It's a binary search tree. If you look at the keys in this tree that I drew here, they still satisfy the property of binary search trees. But on top of that, we have some structural properties. Here we are coloring the nodes of the tree so that we satisfy these 5 properties.